Optically active compounds. In this lesson, we are going to learn which compounds are optically active and which are not, and why. So, let's begin. Let us take two compounds. One is 2-bromo-2-chloropropane. Another one is 2-hydroxypropanoic acid. Let's write the compounds. This is 2-bromo-2-chloropropane. 1, 2, 3. Another one is 2-hydroxypropanoic acid. One, two, three. 2-hydroxypropanoic acid, or simply this is called lactic acid. Now the point is which one is optically active and which one is not. Let's see the matter in a schematic diagram. Suppose this is plane polarized light which is vibrating along a single plane, suppose y-axis, at the time of propagation along x-axis. When this plane polarized light is passed through a solution of a compound A, suppose this is A, then we see that no change in the plane polarized light. That means the plane of the polarized light remains as it was when this plane polarized light is passed through the solution of compound A. That means compound A cannot affect the plane of the polarized light. So we can say that compound A, that means 2-bromo-2-chloropropane, is not optically active compound. But when suppose this is compound B, B is taken in place of A, then the plane of the polarized light is changed in this way. Suppose this is plane polarized light. When it is passing through B, then it is changed in this way with a specific angle. That means compound B, that means 2-hydroxypropanoic acid, affects the plane of the polarized light. As a result, plane of the polarized light is changed with a specific angle. So we can say that compound B, that is 2-hydroxypropanoic acid or lactic acid, is a kind of optically active compound. Now let's try to know why this is optically active and this is not. In compound B, we see that this carbon is linked with 4 different groups: hydrogen, methyl group, hydroxyl group, and carboxyl group. This carbon is linked with 4 different groups. That is why this carbon is called asymmetric carbon, or this carbon is called chiral center. So we can say that the compound with chiral center That means chiral compounds are optically active compounds. But in this compound we see that this carbon is linked with 4 groups that are not different. Here methyl group, here another methyl group. So this carbon is not asymmetric carbon or chiral center. Simply this compound is not a chiral compound. This is the reason compound B with chiral center rotates the plane of polarized light, but compound A no chiral center, that is why it cannot rotate the plane of the polarized light. Because of the presence of chiral center, this is optically active, this is not. Let's see some more examples of chiral compounds, that means optically active compounds. The compound is 2-chloropropanoic acid. Let's write. This is 2-chloropropanoic acid. Here this carbon is chiral center, which is denoted by asterisk. Here 4 different groups are methyl, chlorine, carboxyl group, and this is hydrogen. So 2-chloropropanoic acid is a kind of optically active compound. Let's write another compound. CH3, C, H, NH2, COOH. This is 2-aminopropanoic acid. Here this carbon is a kind of chiral carbon or asymmetric carbon. Here the 4 groups are methyl group, amino group, carboxyl group, and this is hydrogen. So it's a kind of chiral compound. That is why it is optically active compound. Let's write another compound. 2-hydroxypropanol. CHO, C, H, OH, CH3. This is CHO, aldehyde group. This is 2-hydroxypropanol. Here this carbon is chiral center because 4 groups are different: aldehyde group, hydroxyl group, methyl group, and this is hydrogen. So 2-hydroxypropanol is a kind of optically active compound because of the presence of chiral center or asymmetric carbon. Asymmetric carbon with 4 different groups achieves a special characteristic. That is why compounds with chiral center can rotate the plane of the polarized light. That is why the compounds with chiral center, that means chiral compounds, are optically active compounds. Number today, thank you very much.